constant,
white.
but it's going to be young Hall, 2200. I don't really know what that is. I'll find out with you guys.
Yeah,
so,
well,
I know young Hall.
we'll discover it together. Okay, now that I started the recording, so I just wanted to give everybody like a debriefing on what exactly workshops are. So number one, they're optional, like I've said probably several times now, but the intention of these workshops is to make your future projects easier for you because they're going to build off of things that we learn in the lectures and give you some extra time to have some interactions with us if you want to like talk with us about topics that we've learned. That gets into point number two, which is helpful. These are supplementary resources for clarification, reinforcement of new concepts, and one-on-one time. These are also, fun fact, throwbacks. Most of these workshops are going to be based off of past ops projects that we decide to dig up and try again. And also, they're supposed to be fun, of course. Like our competitions, which we don't have one this quarter, but we will next quarter, there are going to be prizes at the end. So keep an eye out for that. Okay. We'll get into workshop number one, Intro to Breadboarding, aka Debugging for Smarties. We've got 3 parts, and I think Eli will get started.
Alright, so as you can see, well, kind of see with this projector, this is a pretty advanced circuit for what you guys have not really seen yet before. But there's actually a lot of errors. And I don't know if you guys could just tell by glancing at it what the errors are. So the point of this workshop is to kind of help you realize it faster. Of course, there's like, you can never be a Flash, but you can be pretty close to a Flash with this help. Alright, so we're going to get started.
You bring mine. Okay.
Alright, so some key concepts that we're going to talk about are elements or components. Those are both terms that we use to describe different things that we put in our circuit. So it's basically any part of our circuit other than a wire. So nothing but like transmit, like a conduit. Like a wire is like a conduit. So an element is like anything that's not a conduit. And then most elements have 2 leads, but you'll learn in future projects that they don't always have 2 leads. They actually have way more than that sometimes. And then examples of these are like resistors, capacitors, RGBs, LEDs, inductors, diodes, your sources, ICs, which that's way getting out of myself. That's exciting.
Next lecture.
Yeah. And then other concepts to talk about is like parallel. Remember that from lecture 2, right? So when components are in parallel, they have the same potential drop across them, but they do not have the same current, right? As opposed to series, when what is it? You guys remember, right? It's like series that have the same current. The voltage is not the same. The duals of each other, the opposites. And then a node, you remember a node that's point of connection and junction, where they connect all at the same point. They all have the same. I like that water flow example, the same tank. Then a voltage divider. This is new. So voltage divider is produces output voltage. That is the fraction of the input voltage based on 2 resistors. We'll actually go into that in the next slide, or like next 2 slides. And then it appears a lot, especially in your intro to circuit classes. And it's like a small larger circuit. Actually, I was just talking with Professor Briggs the other day. He's going to be your EE3 professor. And he's trying to implement a new part to the project that he does throughout the year, which is like making a car using PID control. You'll learn what that is. But he's using a voltage divider for that now too, to track battery voltage. It's a cool concept. I think it's a lot of work for an intro class, but it's gonna be cool. So I'll be excited to see it. And then a DNM, we talked about that too. That's used to track your. Well, actually, I can do so many things now. Impedance, resistance, voltage, current. There's also some that are able to track capacitance and continuity. It depends on it. You can typically tell just by checking it, but it does still say capacitance.
Right.
Other half will capacitors. There are some inductance meters. You don't know what an inductor is yet, but those are cool to experience. I don't know why I have these issues. Alright, so some basic review of what we talked about, right? So a short circuit is when you have two nodes that are connected. Well, actually, yeah, two nodes that are supposed to be two individual nodes, but now they're connected by like one node. So that creates a short, right? That can be very dangerous because if you have a short and you have infinite current, you don't have, let's say, a current limiting resistor in series with that, you're going to have a disastrous event happen if your voltage is too high. Well, it can happen in lower voltages too, but you know, fire, electrical fire, which is what do you not do when you have electrical fire? You don't put it out with water, right? You should know that.
You guys all did the lab safety training, right?
You did lab safety training, right?
Yeah.
Yes, nod your head. Yeah. Okay.
Good.
And then an open circuit, that's just when it's not connected. 9 times out of 10, you'll find yourself making these errors, just like on a wing, especially with the breadboards. And that's mainly because the pins are so tiny, it's going to be really hard to see. I mean, I have 20/20 vision, but it's still like hard. Sorry, so flex. But it's still hard for me to notice when I plug in a thing into the breadboard, and if it's in the exact row or column, which I get to. Columns aren't that bad, but row. Typically, I deal with open circuits when I make an error, but definitely need to watch out for short circuits. That's the worst circuit breaking. Alright, so that's a voltage dividers. Alright, so the diagram on the left, that's a voltage divider, right? As you can see, there's two resistors in series with the battery source. And then we have like kind of these like dashed lines, right? We have one at the top, one at the bottom, one in the middle, one at the bottom. And so what those lines do, we can trace the voltage across these two resistors using not only Ohm's law, but the rules of circuits and equivalent resistance, which we talked about in lecture 2. There's actually all the equations are worked out there for you. But the premise of it is that, thank you.
Yes.
But the premise is that by taking the value of your resistor, actually taking the value of the resistor you want to calculate the voltage drop over, dividing by the sum of the two resistances and multiplying by the source voltage is going to get you the voltage across that resistor. And it's the same for the secondary. So I forgot about that. But as you can see though, that if you have greater resistance, you're gonna have a greater voltage drop across that resistor, right? And then it's the same for like if you change, let's say you increase R2, it's going to be greater than R1. R2 is going to have a greater potential drop across it than R1. And we can actually use this to implement some cool functionality, such as changing the LED. Remember Project 1, how we dealt with the LED, right? We changed we made it light up, right? So, kind of a teaser, but does anyone here know how we can use this to make it have a different so-called light, like make it light at a different brightness? What does that say? Anyone have an idea? No? No takers? No?
Look at this guy behind you.
You just vary the resistance with that vary the current, which then changes the brightness of them.
Yeah, that's good. Yeah, so by changing the resistors on this diagram, let's say we want the drop across R2 to be greater, right? So increase the resistance of R2. What does that mean with the voltage divider? That means that the voltage 2, right, across R2 is going to be greater, correct? Alright, and because of that, and because of the rules we know of parallel, it means anything we connect parallel to R2 is going to have that same voltage drop across it, right? And because of that, by increasing R2, we can increase the intensity of, let's say, an LED we put there too. But always make sure, we have R1, you're fine. You have that current limiting resistor, or we have the resistor for your LED, which you learned Project 1 about. So conceptually, that's a teaser of what we kind of deal with a little bit later on. So.
I think another application that we can think of voltage dividers are like those power source modules that you guys use. So you know how we plug in a 9-volt battery into it, but then we get out 3 volts or 3.3 volts or 5 volts. So the way that works is that there's just a voltage divider inside of that little component, and that divides down the voltage so that it's something that you want to use, not completely 9 volts, but only 3.3 or only 5. So that's the way that that works using one of these. These are really common circuits, so it's good just to like know that formula right there. V out equals V in times R2 over R1 plus R2. All right.
Alright, okay. So you kind of know breadboards in project 1, right? So basic review here is that the center is full of horizontal nodes, right? As opposed to the columns on the side, those are like column nodes, or vertical nodes, yeah. But the power and ground buses, those are the ones that are on the sides. Of course, some people ask me, well, what if I put power in the negative one? Will that create a problem? No, it's just a labeling thing, you know? Let's say I really wanted my 9-volt power source to be connected to the negative or the ground line, right? I could do that if I really want to. I don't know why you would want to, just because it's a little bit simpler using what's given to you, but it's not going to create an issue for you if you do that, because it's just the same copper inside to each other. And note that the columns are not connected to each other, as the rows are not connected to each other, and especially with that center divider. A lot of people also make the mistake of thinking that that center divider doesn't like prevent anything, like that those two like separate rows are connected. No, that center divider divides those two. And all the breadboards you'll deal with ops are like this. I know a few that aren't like this, but typically in like 99% of the applications you'll ever use it's like this. And then yeah, I think that's basically it. Okay, and then again,
I think this is like a straight copy of the lecture 2 slide, but just to kind of rub it in, I guess.
Just like make sure that if you're tracking your voltage drop, right, you put in parallel, correct? So whatever you're trying to track your voltage across. But when you are tracing current, you need to make sure to take out the lead of one of it and make it like a wire. So you need to make track current with the DMM, you need to integrate it into the circuit so that current actually flows through it. Because if you put it parallel to it, it's kind of short. It's going to short through the DMM, okay? So always make sure you put it as a component of the circuit. Treat it like that. As for resistance analyzing, you just need to connect it to, I might say impedance versus resistance. They're the same thing, basically. We won't deal with AC stuff here, but if I say impedance, that's just out of habit. It's basically resistance. So I'm sorry, I apologize for that term kind of popping up. It's just like knowledge here and there. Sorry, and then we won't deal with anything I think above 10 amps ever.
I hope
but
not.
if you're dealing with something above 10 amps, you use the leftmost red probe plug-in on your DMM. For the most part, we use the right one. And then it's also important to note that when you're testing current, you need to start at the highest value that you can, or actually a good practice would be calculate what you think the amperage is going to be, the current's going to be, and then you like put the knob to around like what exponential you think it's going to be, and then move it to adjust. However, if you don't know what it is, or let's say you're being a lazy engineer and you don't want to do the math, start from the highest and go down. Because if you start from the lowest and go up, let's say like I'm trying to track something with milliamps and microamps. Let's say I'm trying to track something with microamps, right? And it's actually like 10 milliamps. The DMM is gonna freak out and blow a fuse, and then poor sap like me or one of the other officers here, you'll have to come up to us and you have to say that you blew the fuse on the DMM, and they'll ask which project you're a part of, and then they'll say ops, and I'll get a message on Discord about how one of the ops kids blew up a DMM again.
Devastating.
And then we'll be trolled by the other officers. So you don't want that to happen to us, let alone that's happened to you. You know, because it depends on the officer. We're all jokesters here, you know. So some of them might like low key like push you down for that. They'll be like, bro, what are you doing? You know. And then
Just ask for help before you measure current. Okay,
Yeah.
that's the point of this conversation.
If you're measuring current, make sure you know what you're doing, because that's the number one cause of breaking DMS.
Yes.
It's just people don't know how to do it. So.
1984. All right, we have an example.
Okay, so actually, I don't know if all of you maybe can join. I'm gonna turn off the light over here so you can see it better. But the example here is asking you if you know what the source of the error in the circuit is. So, someone who has a good idea of what
That looks so much
so
better.
far with breadboarding and basic circuitry, tell me what's wrong with the circuit. Yeah.
The resistor is not in the same row as the LED.
No, that is not the problem. That's
How is it?
It doesn't short across the row because it can just flow like
Exactly. So if we were to like give power to the circuit, what would happen? Or what do you think would happen?
Yeah.
You're right, but I'm just curious.
I would assume the LED would turn on.
Right, exactly. The LED wouldn't turn on. So for those of you who like maybe didn't hear him, basically what's happening here is that LED is both of the leads of the LED are in the same row. So that means there's no like you said, it's being shorted across the LEDs. So it's going to completely bypass that LED and the LED is not going to turn on. I'll just reveal the answer right here.
So remember that current always takes path of least resistance, right? So because both parts of your LED are connected to the same node, it will never go through your LED because your LED does have some like microscopic or like something that we don't really care about, but it does have a form of impedance or resistance, right? And because of that, your current's not gonna go through it. It's gonna be like, oh, I don't like that, so it's just gonna go through like the metal, the copper, and just go straight to the wire. Luckily though, since you have a resistor there, you're not looking at too big of a problem. You're just going to look at it's going to dissipate heat through the resistor. It's going to dissipate that energy. You're good. Now imagine if we didn't have the resistor there. Let's say we made two mistakes. We did this with no resistor. Now you have a completely shorted circuit. So you have, let's say we use that 5-volt source, right? You have 5 volts going basically from 5 to 0. You have infinite current. That's going to be a problem for you. And it can do a lot of things. I've actually, I hopefully will never have to see any of you blow up anything here, but if it does happen, you're looking at probably a fire, but like a micro fire, like a fire within the component itself, like the breadboard might start heating up like a lot. And that's just
Hopefully
because
you will smell the smoke before it actually becomes a fire.
you'll
But
be able to smell it. You'll smell burning plastic. But again, don't try this. Just know. Yeah.
So it wouldn't be like the LED. So if it was just like the power to like the LED in that row, it wouldn't be like the breadboard that burns and not the LED.
Yeah.
Because it would never reason to go
Because
through.
it would never go through.
Yeah, it would never reason to go through the LED.
It would burn through it would burn the plastic around the bread.
right.
Because the electrons are moving so fast through the plastic now. The plastic surrounding that like wire, so to speak, that it's going to heat that up instead. That's a good question.
All right.
If you use regular wires, you'll notice that the heat shrink around it will start to release materials. That's just
Hopefully you won't have to experience that, but
I think I mentioned this earlier, but in my first ever circuit that I did, not you, but this happened to me with an LED because I didn't use the resistor, and the LED just progressively got brighter and brighter, and then it just went out, and then all of a sudden it starts smoking. So and I was and then my teacher was like, "What the heck, bro?" I started yelling. It was funny, but okay. Some new components, guys. These are some things that we're actually going to deal with in the future. It's push buttons and potentiometers. Potentiometers have variable resistance. So what this means is that by turning this little knob, we can change the total output resistance. Well, not output resistance, but kind of output resistance in a way. It's basically at the premise of it. It's you're using a voltage divider, right, to change the voltage that comes out. Okay. So that circuit that we showed you a little bit back with the voltage divider. That's just happening internally here, but with the rotation of the kind of like a disc. We won't deal with the internal controls of it, but just know that's a voltage divider within it, and that's outputting a certain voltage to you. And then push buttons. These are kind of like switches. You deal with switches at your home. You know, you turn off the lights, you turn on the lights. You might have dealt with like switches on your own time. With push buttons, instead of a switch, you have to like hold it. Well, ours you'll have to hold unless you code it to not be like that. We'll get into that later. But basically, you just push it. And it goes across. There's two different sides. Well, I mean, there's 4 prongs to our push buttons. I think A and B are the same in D and C. Is that correct?
Oh no, it's
Or
the
is
other
it
way.
Okay, it's A and C and D and B.
Yeah.
Yeah. So A and C are the same, and B and D are the same. We'll get into that more later. But these are some newer components that we're going to start integrating. You'll also learn that push buttons are the nicest of things because, like your breadboard and your green LED spec, they have problems. And something we'll teach you is how to debounce these buttons. That's a process which we use to make sure that it's more, like, kind of adjust that sensitivity. I don't know if you've ever done that on your controller on like Xbox or something. But to make it so that it doesn't just change rapidly, because sometimes things just happen. And that's just a thing we have to deal with, okay?
Yes. Later on, we will get into that. Later lectures.
And then another component.
Oh, coming in.
Another component will integrate more into lecture and into the projects in the future is going to be RGB LED. It's basically a combination of 3 LEDs. So a green, a blue, and a red. It's easy to remember, RGB. Or Ruth Gator Binsberg. I always call it Ruth Gator Binsberg, but you know, that's my thing.
Red,
So, like LEDs, you need to make sure that they're all connected to a resistor of associated color and magnitude. Typically, it's good practice just to have like a similar one for all of them. You don't really have to calculate for all 3 unless you were given the spec, but always check the spec, you know, because that's like your diehard, right? Always read the spec. And then I guess the question that we have for you is why do we need 3 resistors? Oh, okay, why do we need 3 resistors instead of 1? Like,
anybody want to take a guess?
someone I haven't heard from yet.
It's not that bad, I promise.
Alright, one of the dudes on the couch is gonna have to answer the question.
Why do you think we need 3 resistors for the RGB LED instead of just 1?
Wait, I mean, not really, but like,
So you can see that on the, or I guess you can't really see, but the RGB LED has 4 terminals, right? So it has like 4 wires, and one of those wires is going to be ground, which is just like, you know, a normal LED. The other 3 are going to be each of the 3 LEDs that are like within that RGB LED. So the RGB LED is basically just made up of a red, a green, and a blue LED, and that's why we need 1 resistor for each of those LEDs. It's just all kind of like wrapped up into one little component.
and that way you can make all different sorts of colors, right? So by
Yeah.
varying the, well,
So like if you had red and blue on, then it would be purple.
Yeah.
If you had
you remember primary colors.
no.
Wait, what's the secondary colors called? Do you remember? It's like composite colors.
I think it's like
Cyan.
yellow. Yes,
Cyan.
yeah.
Yeah.
Yeah. And if you have all of them on at the same time, then it's going to be white.
Yeah.
No,
If you have-
green is
yeah.
front lights, yeah. You see?
Is this?
I don't know how colors work. This is not color theory. This is electrical engineering. But
The
you can also like see over here is our switch. So like this is the thing that we're going to be debugging. This is our switch over here, which is like the push button, and these are our 2 potentiometers. So those are all connected up to our RGB LED. That's going to affect how the RGB LED turns on, basically.
And all of the RGB, so even though there are separate, like 3 separate LEDs inside the RGB, note that they all share the same ground. And why is that? Because it's ground, right? Just like make sure you know that. And always the longest LED on your RGB is ground. Okay. Sometimes though, you'll deal with like someone who cut the RGB. In that case, there's a little bit more thought to that. I think, is there footage on the RGB?
I don't know. Probably not.
In that case, you kind of just like cope, you know. But
Yeah. So you'll notice that on a normal LED, it would be the longer lead is the positive and the shorter lead is the negative. On the RGB, it just so happens that the longer lead is the negative. But you know.
But it's easier for you to know, right? Like you can just look at it and go,
Yeah.
oh, okay. Because if it was all the shorter ones, then you'd be like, oh, well, like, you know, there's 3 shorter ones, right?
Mm-hmm.
So then you think that N is the long one. Just don't do that, okay?
Alright, so now we're going to actually get into debugging things. Alright, so first things first, these are just a couple of debugging tips that you should probably keep in mind when we eventually get to debugging that circuit that we showed you at the very beginning. Number 1 is going to be, can I follow my wires? So the easiest way to do this is usually just to start from power and then retrace your steps through each component until you eventually reach the ground, and making sure as you go along that you can follow the same path on your board as you can on your schematic. And if you find that they don't line up, then that means you probably have some kind of error somewhere, whether it's a short circuit or an open circuit. So the next thing is going to be, are your components connected at the right nodes? So this kind of like goes with following your wires. If you reach a point where your components aren't connected at the right node, then you're going to be like, oh, there's an open circuit there, right? So you want to make sure you check your connections, which components are supposed to be connected to that node. Do you have anything that's unconnected? And is the wire at the right pin on your component? So with resistors, the pin doesn't matter, right? But with like LEDs, you do want to make sure that it's at the right one. Okay, next up. Okay, so now we're actually going to try debugging this. I promise it's not that hard. I also placed all of these points so that you could actually see where connections are. So there are 3 main issues with this circuit, and I want you guys to try and see if you can find all 3 of them.
Do you have the slides pulled up? Just like look closer?
Yeah.
But like, if you don't,
Hopefully
totally
that
fine.
looks
Just,
good
like,
enough.
look closer to the screen. You guys should be able to see.
So just like using our tips, can you trace through? And I promise there's no like tricks here. You should be able to find all 3.
One dash two. Oh, sorry. WorkshOPS. One dash two.
There's 1 in each column. It's like column 1, column 2, column 3. Well, just a tip.
There's 2
It's all right.
Oh yeah, this thing down here is the LED. Sorry if that was ambiguous.
How many problems are
There's 3.
Side.
3 ones that are obvious at least.
So basically, it's just a circuit here.
It's slide 20.
You can.
I'm there.
I'll give you guys another minute to think about it, and then we'll reconvene. What is that noise?
Who knows? Who knows?
What could possibly be making a constant? I feel like I'd expect them to be more like banging as opposed to. Does anybody need more time to think about it?
Actually, let's have someone answer.
Oh.
Just
Oh.
no one volunteers anymore.
Well, I don't want to choose.
You want me to choose someone?
If you want, okay.
There's one that's by itself.
Does anyone want to volunteer?
But there's no one that's by itself.
Yep. Okay, go.
Right, so we have this point over here, and it's supposed to be connected to this wire, but we see that the resistor lead is on this row, while the wire is on this row, so that means that they're not connected. Excellent, that is one of them.
Okay, we're gonna have someone else. Good job. Alright, we need another person to find one more error. There's 3 errors total, remember? One more. If you don't volunteer, you're gonna get chosen at random.
Can I try?
Yeah.
Yes.
On the very left, there's 3 in the, is that wrong?
Right, so we have this resistor here, what we'll find is that this resistor is doing nothing because this one over here is connected to nothing. So what we're supposed to do is you're supposed to have this wire connected over here, so that way the current will flow from our potentiometer through our resistor to the wire to our RGB LED. So there is one more error. Does anybody know where it is? Yes, please.
What was the other errors? Because I'm not sure if I remember the error I see.
Oh, the leftmost resistor and the rightmost resistor. So
Yeah.
just since we have two down, the last issue is within the middle column.
Is it the button?
Yes, it does have to do with the button.
Like the resistor is in the wrong row.
Exactly. So we see our button connections are here and here, and our resistor is in the middle row. So that means our resistor is not connected to either lead of the button. So we would have to move the resistor over here or over here. Actually, I think it would have to be in diagonal in order for it to work. Yes.
Also, like I guess the second wire or second cable at the bottom, like it's connected to like the ground row, but like the ground row is going to be connected to.
Do you mean this one? Yeah, okay. So I guess this kind of assumes that this is connected. Oh wait, did you mean that like this is not connected to ground? This bus?
Yeah.
That is an excellent observation. That was the secret problem. So very good job for figuring that out. There's a fourth issue that he found out. We'll go over it. Don't worry. It's that the ground is not connected. Okay. So for those of you who maybe didn't get it and would like to see a better representation, so on the left side over here, we have our resistor that's not being used because the wiring would bypass it. So we'd have to move the wire over to the other lead. Our second error was that we had the resistor not connected to the button, so you would have to move that lead one over in order for it to work correctly. And finally, our resistor over here on the right is not connected to the wire because their leads are staggered, so we'd have to move that wire one over in order for it to be connected. Okay, so even after we did all these three things, we still find that our circuit is not working. And here in this case, I'm using my digital multimeter to measure the voltage across my resistor, and I see that there is no voltage going through, even though everything's connected and everything's turned on. So what could be the issue here? We already identified it, luckily, and that is that our ground is not connected. So we see at the top here, our ground is connected to this top bus, but this lower bus over here, which our RGB LED is connected to, is not connected to ground. So that we usually call this floating. So we say that like this lead over here is floating. And that basically means it doesn't really have a defined voltage, but because it doesn't have a defined voltage, it's not going to want to like flow through. So you'd have to make a connection to the ground bus on the other side over here in order to get ground over here, and then our RGB LED is going to be able to turn on. So that was our full circuit. Does anybody have any questions about how we debug this or any breadboarding things? All good?
Good.
Okay, fantastic. So just a couple more things that I want to talk about in terms of like hardware debugging. So you might have an issue where your components are backwards or burnt out if it's polarized, especially in the case of LEDs, which we've already all kind of gone through with Project 1. But you always want to make sure that you know which end is which. Anode should be closer to the power, and the cathode should be closer to ground. And a burnt out LED isn't going to turn on because it's burnt out. So just always make sure you have a resistor in series. And if you think your LED is burnt out, then like throw that one away and choose a different one. Don't give another person your burnt out LED. Okay, next, is everything plugged in? So this may seem kind of like silly, like of course I plugged everything in, but you never know. Sometimes you just need to push it in a little bit more. So you always want to make sure that you push in your components fully, especially integrated circuits, which we'll talk about more in lecture 3. Using good wires, using solid wires and not stranded. You guys don't really have to deal with that because all of your wires came in your kits, but sometimes we used to have people take the wires from back there, and there are stranded wires, which is like basically like a bunch of little strands wrapped up in a single wire, and those are really hard to plug into a breadboard. But yeah, hopefully you won't have to deal with that. Just unplug things and replug things. Sometimes that's all you need to do, or just use a different row because it might be an issue with that particular hole or that particular row. However, in general, indiscriminately pushing things harder into your breadboard or switching out components is not going to fix all of your problems. This is just kind of like a tip that you should remember if you are having a little bit of issues. Okay, and finally, have I asked for help? Don't build circuits alone. It can get really frustrating, so just make sure you ask us, ask your friends, or other IEEE members or officers for help if you're in the lab working on it. Okay, I think that is the entirety of our workshop. However, we have a quiz with prizes. So if you either click that link if you're on the slides or go to that tiny URL, you can take our quiz. And if you get 100% on it, then we will give you a prize. Prize is undetermined, but
It'll be cool, guys.
it will definitely be
Especially
cool.
'cause all of you showed up.
Yes. It will be yummy at the very least.
Yummy.
Yummy.
Not you.
Alright, and
Is
then in
this-
terms
are
of
these-
what you might be thinking about what the next workshop
Are
might
these
be,
solos?
we are dealing with
Yeah,
very
it's
much
solo, yeah.
technical things on workshops 2. We're going to be building. You're going to have a lot more knowledge on how to build a circuit by then, but we're going to be building a circuit, okay? And then workshops 3, which you won't even have to worry about, so quarter 3. But workshops 3 is a lot more. It's going to be encompassing like everything you've learned plus some. We're going to teach you how to solder. We're going to teach you how to design a little bit with Eagle, which is a PCB designing app that actually a lot of us use here. I used Altium Designer a lot, but Eagle's basically like the encompassable version for everyone. And then we're also going to teach you like engineer's intuition and like thinking outside the box. Okay, it's important to have creativity. So apply that to like anything, but especially in engineering. What's gonna like make you stand out to another applicant to a job, or internship, or anything that you want to go for is not just that you know how to do something. They always want to know that, but can you like think creatively? Can you think out of the box? If they give you like a problem, can you think of a like creative solution to that problem? So just think about that, and thank you all for showing up.
Yes, thank you all so much for coming out. We were really excited to launch this. This is like the first year that we're ever doing workshops or anything like this, so we're really happy that we got a lot of you coming here. But yeah, good luck on the quiz.